internal forces for statically determinate multi-span beams.
Internal forces of a determinate multi-span beam. We should firstly analyze its geometric construction, and then calculate single beams. According to characteristic of determinate multi-span beams, subsidiary portions should be calculated firstly, then the main portions. So the key points are distinguish main portions and subsidiary portions correctly. And we should master the calculation of single beams. Look at an example. Calculate the internal forces of this determinate multi-span beam. Here, two methods will be introduced. One is the free body analysis method. The other is conceptual analysis method. Firstly, let's discuss calculation by using free body analysis method. According to geometric construction, this beam contains two subsidiary portions, ABC and FJH. The part CDEF is the main portion. So we should calculate the two subsidiary portions firstly, then the main portion, CDEF. The free body diagram of each portion could be drawn. For ABC part, there will be reactions at hinge C and support B, FYB and FXC, FYC. For FJH portion, there will be actions at hinge F, FXF, FYF, and the support reactions FYH. So there will be reactions for the main portion CDEF. FYC prime is opposite to the direction of FYC. FYF prime is in opposite direction to FYF.
Here, FXC and FXF are all equal to 0. The support reactions at D and E are FYD and FYE.
For ABC part, according to equilibrium condition, FYC is equal to QL. Because uniformly distributed load Q is equal to 0 for the ABC part, the bending moment diagram of AB and BC part are all diagonal lines. Upper side in tension. MB is equal to QL times L, so that's QL square. MC is equal to 0, so we connected these two sections directly. For FJH part, FYF is equal to half of QL according to equilibrium condition. The bending moment diagram is such a polyline. For the section J, M is equal to half of QL square. For the main portion CDEF part, FYC prime is equal to QL, FYF prime is equal to half of QL. Then for the CD part, because Q is equal to 0, so its bending moment diagram is a diagonal line. According to the direction of FYC prime, the lower side is in tension. MD is equal to QL times 2L, so that's 2QL square. For the EF part, Q is equal to 0, so its bending moment diagram is also a diagonal line, upper side in tension. ME is equal to half of QL times 2L, that's QL square. The bending moment of DE part could be constructed by superposition method. We connect these two sections M directly by a dashed line and superimpose a parabola because there is uniformly distributed load Q acting on this part. The ordinates here is Q times 4L squared over 8, so that's 2QL squared. According to the bending moment diagrams, we could construct shear force diagrams. For ABC part, the bending moment diagram is diagonal line, so the shear force diagram must be a horizontal line. The slope of bending moment diagram for AB part is QL squared over L, so that's negative QL. For the BC part, the slope of bending moment diagram is also QL squared over L, so that's positive QL. For the FGH part, the bending moment diagram is a polyline, so its shear force diagram must be horizontal line. According to the slope of bending moment diagram, FG part and the GH part, we could obtain the shear force is positive half of QL and negative half of QL. For the main portion, we could obtain shear force diagrams for CD part and EF part. They are all horizontal line parallel to the axis of the member. The slope of bending moment diagram CD part is 2QL squared over 2L, so that's positive QL. For the EF part, the slope of bending moment diagram is QL squared over 2L, so that's half of QL, positive. For DE part, according to the bending moment diagrams, we could draw its free body diagram. The shear force of section D and E could be calculated according to equilibrium conditions. That
FQDE is equal to negative 3QL squared over 4L plus 4QL over 2L. That is 5QL over 4.
According to sigma Fy is equal to 0, we could solve FQED. That's equal to negative 11QL over 4. According to the two values, we could construct the shear force diagram for the DE part. Because Q is a constant, so its shear force diagram must be a diagonal line. At last, we should give the sign for the shear force diagram for each part.